Hello everyone, so today we are talking about operations with radical expressions. In the last section we talked about taking nth roots, and some of those rules we're still going to be seeing here, but we are also going to be doing operations like adding, subtracting, multiplying, and dividing with radicals. So we are going to use the same rules to potentially use those absolute value bars as we talked about in the last section, and remember that is when your index is even, your power on the inside is even, and your power on the outside, once you simplified, is odd. So do be careful and do watch out for that, but you only have to worry about it when your overall index is even at least. So let's take a look at the first one. We will see in this section that sometimes our radicals won't simplify perfectly like they did in the last section, but that's alright, we can roll with it. So simplify square root of 25, a to the 4th, b to the 9th. So, well, I can take the square root of 25, that's just 5. Square root of a to the 4th, a squared squared is a to the 4th, so I know that's going to be a squared. For b to the 9th, or realistically, anytime you're dealing with these exponents on these variables, if you want to make it easier on yourself when you're mentally thinking about it, instead of thinking, okay, what power squared gets me like something close to that number, if you do a short long division, so that's my exponent on the inside, I'm dividing by 2 because I have a regular square root. I have 4, remainder 1, so b to the 4th is going to come outside, and square root of b to the 1st is going to stay on the inside. So it's just kind of a little trick to help you simplify those guys, especially when we see something like in the next one. Now do notice in this one we did have an even index. We had one of our exponents on the inside be even, but it came out as even as well, so we didn't have to worry about that absolute value case. Let's take a look at our next one. So we are taking the 4th root, so another even index. We might have to worry about potentially that b, because that's also an even in there. So we're going to take the 4th root of 625, that is 5. 4th root of b to the 28th, I'm going to use that little division trick that I just showed you guys. So if I take 28 divided by 4, well, it goes in evenly and it's 7. I noticed that that even power on the inside became an odd power on the outside, so I'm going to go ahead and put those absolute value bars to make sure I'm talking about my principal root there. And then for k to the 23rd, 23 divided by 4 goes in 5 times with a remainder of 3. So I'm going to take out a k to the 5th, leave my 4th root, k to the 3rd on the inside. Do be careful, particularly when you're simplifying these radicals that have an index that is something other than 2. You do need that clarifier that's a 4th root. If you have it as a square root, I am going to have to take a point off because it's not a square root. You totally change the problem if you change your index. So just be careful about that. If you need to bring a highlighter in a quiz or test and highlight any sort of awkward indexes, go for it. That's fine. Just be careful. So let us move on. Multiplying. You've seen this. The only thing that you probably haven't seen from Algebra 1 is the, weird index here. So I'm going to walk through by just multiplying through what I can and then simplifying. If you prefer to simplify, if something simplifies where you already are, so say, in this case nothing does, but say, we could take the cubed root of 100. You can simplify that and go on your way and then multiply and then simplify again, or multiply through and then simplify in the end. So let's take a look. I have 5 on the outside, which is going to stay on the outside. I've got the cubed root of 100 times 10. Those are both inside the radical. I can multiply them. And then a squared times a is a to the 3rd. Luckily for us, these all simplify. So I've got 5 times, the cubed root of 1000 is 10, and the cubed root of a cubed is a, so I have 5 times 10a, which is what that radical was simplified, so I have 50a. And that's all that one is. In this next one, I've got 2 coefficients in front of some radicals, so I'm going to multiply those. Multiply my radicals on the inside. This is what I meant by like the simplifying as you go. If you want to simplify that square root of 8 before you multiply, that's fine. I have nothing against that. Just be careful when you're moving numbers around to keep track of everything. So I've got 2 times 8, which is 16. C to the third times c is c to the fourth. And then d times d squared is d to the third. Simplify everything that we can. So I've got 18 times square root of 16 is 4. Square root of c to the fourth is c squared. Don't have to worry about the absolute value bar on that one because that power on the outside is even. Square root of d to the third, well, 3 divided by 2 is 1, remainder 1. So 1's going to come on the outside. And remember, even though we are taking a square root here, so you would think, oh, I need an absolute value, but the power on the inside was odd, so you don't have to worry about it. And then square root of d remains on the inside. So 18 times 4 is the only thing that we can simplify there. So 72, c squared, d, square root of d. Next, we're going to be talking about some addition and subtraction. Now these you can only do with like simplified radicals. So looking at these, you might be like, oh, none of those are the same, can't do anything. But they do simplify. For example, square root of 48 is the square root of 16 times the square root of 3. So I'm going to take my 2 times my 4. So I've got 8 root 3 minus square root of 75. Well, that's the square root of 25 times the square root of 3. Square root of 12. What looked like unlike radicals from the beginning ended up being like radicals after all. So I've got 8 minus 5 plus 2. In the end, I have 5 root 3. Now the next one's kind of an example of multiplying and simplifying with adding and subtracting. So just FOIL. Notice numbers on the outside do not multiply with numbers on the inside, so that got us the 3 root 2. And then square root of 7 times square root of 2, we were able to simplify those as square root of 14. So numbers on the outside stay on the outside, numbers on the inside stay on the inside. I'm looking at this, well, only possible way this would simplify if the square root of 14 had a perfect square factor, which it does not. So, as bizarre as that looks, that is indeed simplified as it is. Now dividing. So, pretty much what this little key concept that you would see in your book is telling you, it's just saying sometimes it's advantageous to, if you have radical both on top and bottom, to divide them first. So if I had the square root of 27 over the square root of 3, you could go ahead and rationalize, as we'll look at in a second, or you can recognize that, oh, if I take the square root of 27 divided by the square root of 3, divide my numbers first, 27 divided by 3 is 9, square root of 9 is 3, makes my life easy. In the next one, on the other hand, it's going to be advantageous to leave those alone, since I can't take x to the 6 divided by 8, and if I take the cubed root of each of those, I can just take care of that from there. So, this rationalizing thing should sound familiar. We've done it a couple times, a little bit at the beginning of the year. We also talked about it with those imaginary numbers. So, pretty much, if your denominator is, just say, the square root of b, you're going to multiply your numerator and denominator by the square root of b. That'll make it so that you have the square root of something that is a perfect square, and your denominator radical will go away. If you have this lovely case, where you have cubed roots or fourth roots or anything like that, you do have to make sure that you're not just multiplying by whatever your denominator is, because that's not going to necessarily give you a perfect cube or perfect fourth or perfect fifth to simplify. And we'll look at that in a second. You can kind of use this formula to sort of gauge what you're supposed to do, but I'll show you an example so it'll make more sense. And then if you have the square root of b plus a number, or the square root of b minus a number, or the square root of b plus, say that number is a square root or anything, you are going to do that conjugate. So if it's a plus, you're going to make it a minus. If it was a minus, you're going to make it a plus. So let's take a look at a couple examples. So in this case, I see I just have a square root of 2 in my denominator, so I'm going to multiply by square root of 2 over square root of 2. So I've got 3 square root of 2 over square root of 2 times square root of 2 is square root of 4, which is just 2. That doesn't simplify, so that's my final answer for that one. In this next case, I see, well, I do have the square root of something over the square root of something. It's going to be a lot better for me to take the square root of them individually, since 25 is a perfect square and 36 is a perfect square. So let's take a look at that. So square root of 25 is 5, square root of 36 is 6, square root of r squared is r, because I had that case with the even index, even exponent, odd exponent on the outside. I do need that square root. And square root of t is not going to simplify for us, so we'll just kind of leave that there. On the left here, we have that case where we have something added or subtracted with a square root in our denominator. So we're going to multiply by the conjugate. And remember, all that is, you switch the sign. Essentially, you are forcing that difference of two squares. So I have 12 minus 4 root 2 over 9 minus 3 root 2 plus 3 root 2. Notice how those drop out. And then minus square root of 4, which is just 2. So these drop out. These, I do not subtract them. Do not write that as 8 root 2. That is 12 minus 4 times the square root of 2. These go together. If you need to put parentheses around them, go for it. But you cannot, by any means, break the order of operations, which multiplication would come first, and subtract those. It's tempting, but you cannot. And then 9 minus 2 is 7. Now this last case is that ugly case that I was kind of talking about earlier. So I can't just multiply by 4th root of 3x over 4th root of 3x. It's not going to get me anywhere. 9 is not a perfect fourth. X squared is not a perfect fourth. I need to multiply by something that's going to get me a perfect fourth. You can use that formula above. I kind of do it mentally, playing around with, well, what's the lowest perfect, in this case fourth, that's going to get me to where I'm going. And that's going to be, well, I have one of them. I need 3 more. And then same with the x. I have one of them. I need 3 more. With the little formula, I would take 4 minus, this is 3 to the first, so 4 minus 1 is 3. We'll practice that more in class, I promise. So, I'm going to multiply across. I have 2 times 3 to the third, which is 27. 2 times 27 is 54. So I have my 4th root of 54. X to the third stays. This will finally simplify for me. So I have 3x. Now, you may wonder whether or not I need a absolute value bar, because, well, I did make it next to the fourth, but because initially it was to an odd power, I don't have to worry about the absolute value bars. If that was initially like an x squared, that would be a different story, and then we would be working with that case where we would need our absolute value bars. We will practice more with this, but until then, I'll see you in class.